Hello and welcome to this clip looking at how we can use thermal decomposition to identify an unknown carbonate. The basic reaction is metal carbonate breaking down into a metal oxide and carbon dioxide gas. So let's have a look at the reaction in detail. What happens is the reaction uses heat to break the ionic bonds in the metal carbonate lattice, leaving the metal oxide behind and releasing carbon dioxide gas. The stoichiometry is the same whether you look at group 1 or group 2 carbonates, and obviously you need heat because breaking bonds is an endothermic process. So the connection between decomposition and heat, in the case of carbonates, is in a carbonate ion, the electron density is normally spread over the ion or delocalized. So you can see there that the position of the double bond can change. Therefore, this means that the electron density is spread over the area of the ion. This is called resonance. Now, if the carbonate ion is bonded to a cation, the cation's positive charge can polarize the carbonate, in other words, draw the electron density towards the cation, and that can reduce the effect of the resonance. So, going from beryllium up to barium, so descending the group, the smaller the ion, the greater this polarizing effect, as the 2+ charge is concentrated over a small volume. So, going down the group, you get decreasing charge density on the metal ion, so less ability to polarize the carbonate ion, like we just said. So what happens is, as the carbonate ion is polarized, it becomes unstable, and therefore electrons can move from one part of the carbonate ion to another, like so. Now what happens if this takes place is carbon dioxide is produced. Now in an experimental setting, this is lost as gas, so the mass of the sample decreases as this happens, so this can be measured. What's left behind is a metal oxide, because you have an oxide ion remaining, plus the group 2 metal ion that you started with. And the formation of this product needs less energy to happen if the carbonate ion is more polarized in the first place, due to the metal ion having high charge density. So the evidence that supports this can be looked at. As you decrease the group, it becomes harder to break up the carbonate into a metal oxide and carbon dioxide gas, because CO3 2- isn't being polarized as easily. So just revisiting that, high charge density for beryllium, low charge density for barium. So in the case of beryllium carbonate, the carbonate ion is more easily polarized, so it takes less energy to break it up. And it's the opposite for barium carbonate. So if we use the reaction to identify the metal carbonate, here's how we can do it. So we heat to constant mass, and as we do so, the CO2 gas is given off. Once constant mass is achieved, obviously no more CO2 is being made, so we've made the metal oxide completely. So here's the procedure. You weigh the crucible on its own, record the mass, add your anhydrous metal carbonate solid. It can't have water crystallization because that would distort the results. You weigh the crucible plus the anhydrous carbonate and record that mass. You then heat to constant mass, so you have at least 2 consecutive masses that are the same. So I've put some sample data in there, and you can see that the constant mass is 39 grams for the crucible plus its contents. So now you can calculate the mass by difference of carbon dioxide lost, and then convert that to moles. And using the stoichiometry of the decomposition reaction, you can calculate the moles of metal oxide left. From this, using the relative atomic mass of oxygen is 16, the relative atomic mass of the metal, the unknown metal, can be obtained, and then its identity deduced from the periodic table. So let's have a look at how this data could let us do this. So, firstly, we have 0.25 moles of carbon dioxide produced because we had 11 grams made. 11 over 44 makes 0.25. From the equation for a group 2 metal decomposition, you can see that the number of moles of the metal oxide would also be 0.25 moles. So the mass of metal oxide left happened to be 10 grams. So if we take 10 grams and divide that by 0.25 moles, that gives us 40 grams per mole for our metal oxide. Subtracting 16 away from that, that means we're left with 24 grams per mole for the metal on its own. A quick check of group 2 in the periodic table allows us to see quite easily it's likely to be magnesium carbonate as the original carbonate that we heated. Okay, I hope this has been a useful overview of how this might work in a lab setting. Thanks for listening as always, and until next time, see you soon.